So I was going to be talking to you guys today about some work that we've been doing to try to understand more about how to develop algorithms and algorithm validations that consider user psychology and psychological research methods. Let's see if I can do this. So many of you guys here today will be familiar with the idea that often when we're making recommendations, we take advantage of some concept of the similarity between items. The problem is that both the item-item similarity algorithms that we use, as well as the methods that we use to evaluate those algorithms, often fail to account for critical aspects of user psychology. So we attempted to build on these limitations in a couple of ways. The first thing that we wanted to do was to develop a psychologically informed similarity metric that took advantage from research in the field of cognitive psychology. The second thing that we wanted to do was to develop a way to do methodologically sound user testing that takes advantage of best practices in psychological research methods. And then the last thing that we wanted to do was both apply this psychologically informed similarity metric as well as our user testing framework to evaluate user judgments of the similarity between specifically fashioned items. So to start, I'm going to get into the details in a second, but I first wanted to provide you guys with a motivating example to illustrate some of the quirks of how humans make similarity judgments. So if I said to you, Jane runs like a cheetah, intuitively, most of you guys are going to know what I mean by that. But if I said the cheetah runs like Jane, that's just a weird thing to say. So we can all see that intuitively, that, to put this more formally, the similarity of Jane to the cheetah is not the same as the similarity of the cheetah to Jane. So what we have here is user judgment asymmetry in similarity judgments. And there are a number of these quirks in terms of how humans judge the similarity between two entities. So how do we actually build a model that takes account of these things? Well, fortunately, in the field of psychology, they've long been studying how do humans make these kinds of decisions. So what I've got here is a pretty old model. I go back. Oh, there we go. A fairly old model from the behavioral economist Amos Tversky for user judgments of similarity. So given that you have two items A and B, you've got the shared set of features of A and B, the distinctive features of A, and the distinctive features of B. What you'll see is there are a number of parameters here. First we've got theta, and what this does is it accounts for the weight of the common features of A and B. We also have a weight for the distinctive features of A and a weight for the distinctive features of B. The reason why these parameters are important is that research has shown that when humans are asked to judge how similar two entities are, they tend to focus more on the common characteristics than the distinctive characteristics. Also, allowing these distinctive features of each of the entities to vary based on these weights enables this asymmetry that I illustrated to you guys earlier. Lastly, you'll see that there's a salience function f, and what this enables is that in any given judgment, some item features are going to be more important than others in determining how users make these judgments. Okay, so I just wanted to point this out to notice that all of these features of the Tversky model that account for these psychological quirks, they're not represented in something that's more commonly used like the Jaccard similarity metric. Okay, so we have some basis on which to build a psychologically informed similarity metric. How do we actually ask users about their judgments for similarity in a way that's methodologically sound? What we can do here is draw from paradigms that come from behavioral and neuroeconomics, as well as some other fields. So what I'm showing here is an example of a forced choice design. So in this, I might ask you a question like, would you rather have 2 apples or 1 orange? And the reason why this is good is that you don't have to worry about absolute preferences. You're dealing with relative preferences within this context. This is also good because more typically you might see someone ask about preferences and rating them on a 1 to 7 scale scale or a 1 to 5 scale. And there are a number of methodological problems with how people use those scales that we avoid in a context like this. So translating that into something where we're judging similarity, what we could do is ask users, given the stress on the top, which of these two on the bottom is more similar? This would be a pretty good way to do it, but it's not particularly ecologically valid. So we can modify that to say, imagine that you're shopping and this one on the top is out of stock. Which one of these two on the bottom is a better substitute? So there are actually a couple of other things that we did in our task to account for the fact that sometimes people aren't necessarily doing a good job at the task. We had 2 conditions that we also showed users where there was an explicitly correct answer, and we used these conditions as a way to screen out users who probably weren't providing high-quality responses. In order to implement this, what we took advantage of is JSPsych, which is a JavaScript library for building psychological tasks, and we hooked it up to Amazon Mechanical Turk to implement this task. We had a couple features of the task that enabled us to control some aspects of our participants. So we're asking about women's stresses, so our participants had to report being female. We also had a couple of other comprehension checks to make sure they could understand the instructions and perform the task. So now that we have this method for assessing human similarity judgment, we wanted to actually evaluate it. So our paper involves a couple of different analyses, but I'll focus here on one. In our model evaluation, what we did is we allocated 80% of our users to training data and 20% to test. And then we were able to operationalize this Tversky model I showed you earlier on the training data. And then we were able to use these model parameters that we derived through that process and predict on our test data. And then we could compare how well the Tversky model did in comparison to a standard Jaccard similarity metric. So I'll walk you first through the parameters that we found in the training data for the Tversky model. What we found is that largely our model parameters confirmed what we would have expected based on psychology. So right up here we have theta, and it is larger than alpha and beta, supporting the notion that common characteristics were more important than distinctive ones. Secondly, what we saw is that alpha is greater than beta, supporting this idea that there is decision asymmetry and that the features of the target were probably more important than the alternatives. Lastly, if you look across these values here, some features were clearly more important than others, and this makes sense. So people are going to care more about whether a dress is black or white than they are about whether it has a collar or a V-neck. When we actually performed the direct model comparison, what we saw is that the Tversky model did in fact outperform the Jaccard similarity. So we wanted to know a little bit more about why this might be the case. On the right here, I have a plot of Jaccard similarity versus Tversky similarity, and you can see that at the extremes, these metrics tend to agree. Where they differ is kind of in these more ambiguous judgments, which is where we're getting our performance lift. So just to show you guys one example of this, this is one user decision and how these metrics performed. Because these 2 items that are the alternatives have the same number of characteristics in common, the Jaccard similarity can't differentiate between the 2 of them. But because the Tversky similarity has these other features built into it, it actually did a better job and assigned a higher similarity score to the option that the user actually chose. So in summary, both algorithms and their validations should account for users if they are in fact going to touch users. And by doing so, we can deliver better products.
So we have time for questions.
Thank you very much. So for people that come more from kind of web analytics and data science, how do you come up with those hypotheses from psychology? Because you can try various things. Maybe some are obvious, but in a new domain and so on. So how do you approach it? I know it works, but you can go into a direction where it just completely detracts you.
So just to make sure I understand your question, you're asking like how would this apply in a different domain?
Yes, how would you start with the hypothesis coming from psychology?
Sure. I mean, so in this case, I think we would have many of the same hypotheses. What would differ would be the features. So for antiques, you know, there are different features that matter for antiques versus the features that matter for fashion. The Tversky model was like a generalizable model. It wasn't built for fashion. So I would expect, although that would be a testable hypothesis, that we would expect to see similar things.
So it gets very domain specific, like.
Yeah, I think in order to tune the parameters, you would have to do that in a domain-specific way. That being said, you could use this kind of information about alpha versus beta and theta versus alpha and beta to set a priori some parameters that might work well in a different context like antiques.
Thank you.
Yeah.
Question back here?
Thanks for the presentation. I have a question regarding features.
Sure.
To get this,
I'm sorry, I couldn't quite hear that.
how hard is it to get those features? I mean, how costly is it? And
Yes.
do you plan to expand the set of features?
This is a really good question. So I neglected to mention that in our case, these features were provided by human annotators that were trained in a proprietary fashion analysis system. So it is very labor intensive to get these features for very large data sets. That being said, I mean, once you have humans provide thousands of labels, eventually you can find a way to automate that. So in the future, we may be able to either automate some of these features or include other features that are more automatable.
Do we have a question in the overflow room?